Okay, in this episode of Talk the Thought Process, we're going to talk about how chemists use quantum numbers to kind of identify the electrons in an atom. It's going to be very confusing for students because it's kind of like learning a new language, and it's just a little jargony. So I think it works best if we can kind of work through building up the atoms one at a time and showing how the quantum numbers are used. So remember, chemistry is all about the electrons. Stuff happens because of the electrons. And that's why we're taking so much time to understand where the electrons are in the atom and how they behave. So there's all this important terminology. First of all, the electrons are not in orbits. They're not like the moon circling the Earth or the Earth circling the sun. They are in these things called orbitals. And the orbital is a mathematical function that describes the three-dimensional space that an electron is in. Right, so electrons are kind of moving around and you can't really nail them down, but they're in a particular space. And that particular space is called an orbital. And these orbitals are described by a set of quantum numbers, and we identify each electron in an atom by 4 quantum numbers. And every electron has its own unique set of quantum numbers. And these are what they are called. This is N, L, M sub L and M sub S. That's how we say those terms. And so if we wanted to identify a particular electron in an atom, we would list these 4 in this order, the 4 quantum numbers. Now here's the definition of those quantum numbers, what their names are and what they indicate. And again, this feels really jargony, and you can find it in your textbook to understand what all of these things mean. But in this episode here, we just want to use them in building up the atom to kind of show more how they work, right? So these are their names and what they indicate. And then these are the rules for what these numbers can be, these quantum numbers. They're small numbers, whole numbers, or the plus 1/2 and minus 1/2 here for M sub S. We're just going to kind of demonstrate how we use them to build up the atom. And here is a table from the book Chemistry and Atoms Focused Approach, which tries to show you how we do that, where we have the quantum numbers N and L and the possible M sub L's in there. And this is one way to look at it. But what I want to do is kind of help you to think about this one atom at a time. So you can get used to using these numbers and see that there's a pattern here rather than trying to memorize this table. So I always say begin at the beginning and then build more and more complex atoms. So when you begin at the beginning, you can just say these electrons are arranged in shells, right? So think of them like a shell that goes around the nucleus of the atom. And luckily, these shells correspond to the rows in the periodic table. Periodic table is a beautiful thing for that reason. Now just remember that every shell that you add adds more complexity to the structure of the atom. So we're going to start at the beginning with the first shell, which is the most simple. Right, so importantly, the row represents the shell number. So our first shell is 1. That's where N equals 1, the principal quantum number. And you'll see in that row we have 2 atoms, hydrogen and helium. The atomic numbers are 1 and 2, so we have 1 electron in the neutral atom of hydrogen and 2 in the neutral atom of helium. And so let's first look at those quantum numbers that describe those elements. So again, think simply. The first shell is the simplest shell. In that first shell, there is only 1 subshell. That's an orbital called an S orbital that has a spherical shape. So I like that S, I guess S is for spherical. Now there's only 1 orientation of a sphere in space. So there's only 1 orientation of the S orbital, and there's only 1 S orbital in any given shell. There are 2 electrons that can occupy any one given orbital having opposite spins. And so as we build things up, you'll see that we put 2 electrons in an orbital in order to build up the atom. So we're going to start with a simple example of hydrogen and helium. So again, hydrogen and helium are the first 2 elements, and here we're just going to make a table that shows the 4 quantum numbers for the 1 electron in hydrogen, right? The first element in the periodic table. First, it's in the shell of 1, right? So this here represents the shell, and this is 1, the quantum number 1. It's a s orbital, and so this is represented by the quantum number L. L equals 0 means it's an s orbital, and there's only one of them, and so we designate that with the simplest number, which is 0. M sub L equals 0. And then the electron in there, we can give it the sign or the quantum number for the spin of +1/2. So this would be the 4 quantum numbers that we can use to designate the one electron in the atom of hydrogen. See how it works? And now when we go to the next electron, the next atom, which is helium, is going to still have that one electron in there that we've designated like this, but it's going to have now a second electron, right? And that second electron, it's going to have the same quantum numbers as the first one, except for the spin is going to be -1/2, right? The same ones because it's still in row 1, n equals 1. It still is in an s orbital, which is spherical, and is designated by the quantum number L equals 0. There's only one of them, and so the m sub L is still 0, and we have to give it the -1/2 because no two electrons can have the same quantum numbers. Everyone has a unique set of quantum numbers. And so these are the 2 electrons that are in helium, right? One that's in hydrogen and another one added to it. Right? And so that's the simplest one. There's one shell, there's one kind of subshell, there's one orbital, and there's 2 electrons. And those 2 electrons kind of correspond to the 1 electron in hydrogen, and then there's 2 electrons in helium. Now, as I said, when we add shells, it becomes more complex. And so we can see here that in the second row, instead of just 2 elements, we have 1, 2, all the way across, 3, 4, 5, 6, 7, 8. So that's what I mean by more complex. So here, in that first shell, we had one type of subshell. We had one orbital called S that has a spherical shape. We had one orientation for that s orbital, and we put 2 electrons in that s orbital. That's how we got hydrogen and helium. Now, when we go to the second shell, we're going to have 2 types of subshells. We're going to have one of them that looks just like the one we used up here, with the s orbital. So we'll have one orbital called an s that has spherical shape. There'll be only one orientation, again, for something with a spherical shape, and there'll be 2 electrons in that one s orbital. But we're adding complexity as we add each shell. We just don't add a shell, we add more complexity. So in addition to that one s orbital, we're adding 3 orbitals that we call p. The p orbitals have a dumbbell shaped, and there are 3 different orientations of the p orbital that we can think of on the axis around the nucleus of the atoms, the 3 axes. And because there's 3 orbitals and we can put 2 electrons in there, each one, then we can have 6 electrons that can occupy these orbitals. So that's what I mean by adding complexity. When we get to the third shell, we will have a subshell that looks like the S, a subshell that looks like the P, and then we'll have another subshell, which is the D. And instead of 1, 3, we'll have 5 of those. So you'll see how the complexity is added with each shell that we enter. Okay, so if we go to lithium, where lithium is the next one, right? So here's lithium after helium. What will the electrons in lithium look like? What will their quantum numbers be? Well, we'll still have the 2 electrons in there that we had put in for hydrogen and helium. They're still there. And then the third electron now we put in, it's in shell 2, right? The second row. So that is now a 2 instead of a 1. It's still an s orbital, so it's spherical, and the L quantum number has the number 0 designation. It has only one orientation in space, and we designate that by 0. And again, we can label that first electron as +1/2. Okay, so again, looking at the periodic table, we're now right here by lithium, and we put electron in there. And so now what you can see here is that when we add the next electron for beryllium, we're also going to put that in an s orbital. And so we see the periodic table is sort of divided into these blocks, right? And the blocks represent subshells. So everything in here represents electrons that are going into an s subshell. Over here, the p subshells. In the middle, the d subshells. And down here are the f's. So that also helps us to understand our periodic table. So now when we go to beryllium, right, we still have the first 3 electrons that we've been using. We add now 1 more. And again, it has the same quantum numbers as the previous one because it's in the second row in an s orbital that has only one orientation, but we have to give it the opposite spin because, again, no 4 electrons have the same spin. So there we have it. We've built up 4 atoms, 4 electrons for beryllium, and we keep going from there. So now what happens when we get to the 5th, right? The 5th element is going to be here. That would be boron. Okay, what's boron going to look like? Well, in boron, I still have the 4. I've added now the next one, and it's going to go into a p orbital. So we're going to put it here. The end is going to be 2 because it's in the second row. But now it's in a p orbital, and the p orbitals are designated by L equals 1, right? So S, the simple one, is 0. P, the more complicated one, is 1. The p orbitals can have 3 different orientations. There are 3 different ways we designate the p orbital. And so one of them is -1. The 3 ways are -1, 0, and 1, right? So there is only 1 for the S, and it's designated 0. For the p, there's 3, and it's 1. It's -1, 0, and 1. Okay, and so now we can add the rest of the electrons, right, all the way across to this is the 5th one, the 6th, 7th, 8th, 9th, 10th electrons, all the way till neon. So we can just kind of add to this table, right? So if we add to this table, we're still in the second row. We're in the p subshell. And then we can go ahead and put this in the 0 orbital and then designate that electron plus 1/2. That's another p electron. Then we add the next one, second row. It's a p orbital, so L equals 1. The m sub L, we can put plus 1. So there we've designated the 3 orientations of the p orbitals as -1, 0, and plus 1. Those are the allowed quantum numbers for that level. And then again, we can put the plus 1/2 for here. Okay, so where are we then? We have 3 more electrons, and we can put them in these orbitals here, except we just have to change the m sub s to -1/2. So let's do that. We'll have 2, 1 for the fact it's a p orbital, -1 to indicate the -1 orientation, and then we'll have to put -1/2. The next one, again, in row 2, 1 because it's a p orbital, 0, and then the -1/2. And then the next one will be 2, and then 1 because it's a p orbital. We can put in plus 1 to indicate that orientation, and then this is -1/2. Right, so again, every electron, and now we have up to 8 electrons in our neon atom, has a different set of quantum numbers. And the quantum number tells you different things: which row it is in the periodic table, which is which shell it's in, what type of orbital it is, the shape. 0 means spherical, 1 means p, dumbbell shape. There's number of those types of orbitals. There's only 1 s orbital. There's only 1 orientation, so they all have the same quantum number for orientation. For the p's, there's 2. So this number can be -1, 0, and 1. And then for each orbital, there are 2 electrons, and we put 1 in at +1/2 and 1 in at -1/2. So you see what I mean by adding complexity, right? Starting with the simple and then adding more. And if you look at this table here, you can see kind of what I've shown you in the table. When n is equal to 2, and you have a p orbital, L is equal to 1, and then the m sub L can have these designations, -1, 0, and plus 1, and then you would have to put an electron in each with a spin +1/2 and -1/2. So this table can be helpful as well. Later on we'll be going on to the d orbitals, but that's the thought process, understanding what each quantum number means, that every electron has a unique set of quantum numbers, and that these quantum numbers correspond to the various places in the periodic table.